Hey guys, so today we're going to be looking at some force problems. We're going to be looking at inclined planes, pulley systems, a mix of the two, as well as some general force problems. And for all of these problems, we have to keep in mind Newton's second law of motion, which states that the summation of the forces acting on an object is equivalent to the object's mass times acceleration. And we also have to keep in mind that, like in kinematics with acceleration, we can have both x and y acceleration. So since acceleration is caused by the summation of the forces, we can have summation of the forces in the y causing an acceleration in the y direction, and we can also have a summation of forces in the x causing an acceleration in the x direction. So we have two different dimensions to our force and to our acceleration, just like in kinematics how we had a acceleration, an x acceleration. For example, whenever we had an object falling straight down off of a cliff, we only had y acceleration while there was no x acceleration. So now we're going to be looking at this problem in which we have a pulley with two masses on an inclined plane. So whenever you're solving these problems, you really want to draw all the force vectors for the problem in order to make sure that you don't leave out any forces and to know which ones are in the y direction, which ones are in the x direction. So let's start off with M2 since it is probably the easiest. So we know that there is going to be, this isn't working very well, we know that there's going to be a force of gravity, which is going to be equal to m2g, since force gravity is equal to the mass times gravity, acting downwards on m2. And we also have a force tension acting on, and the force tension is really caused by the other mass being on the cord, which is basically resisting the second mass from accelerating downwards. And notice that my vectors are not the same length. Vectors indicate not only direction but also magnitude. So since I know that m2 will be accelerating downwards, I have the acceleration right here. That means the force gravity must be greater than the force tension. I gave the example perhaps in another video, but we have a cord with two different people on it. One side of the cord is someone just a little bit stronger than the other person on the other side of the cord, and they're pulling in opposite directions. Since the person on the right side of the cord or rope is stronger, he will make the rope move towards his direction, but it will be impeded. It will be a little bit harder since there is a force acting in the other direction. Therefore, this is the same thing. And if I were to take my force gravity, subtract that from my acceleration, I'd get my force tension vector. So you really have to keep in mind that the vectors are not just for direction but also for magnitude. So draw them accordingly. Okay, so now we drew all our forces acting on M2. Now let's look at the forces acting on M1, and this is going to be a little bit more complicated. However, we are assuming that there is no force friction in this problem, so M1 will have no force friction. And in real life, there would be friction along the cord, but we're not going to take that into account. So now, we know that, first off, that force of gravity acts downwards all the time. So we can draw that right away. However, our force of gravity in this situation isn't acting straight down or straight horizontally in the x, but rather, since we're on an inclined plane, we have x and y coordinates based on the surface of the incline. So we shift our x and y coordinates based on the incline. The incline now becomes our x coordinate for gravity, and our y coordinate for gravity becomes the perpendicular line to the surface of the inclined plane. So now we're going to do a little bit of geometry in order to solve our components. So also, this should be on the object, but I'm drawing it a little to the side to clarify for you guys to be able to see the vectors. We also have a force normal acting perpendicular to the surface. And in other problems, whenever it's on a flat surface, the force normal is typically in vertical, but since it is perpendicular to the surface, that would not be the case for here. So whenever you're looking at force gravity, you want to divide it into two different components. You want to divide it into a parallel force gravity, or a perpendicular force gravity, and a parallel force gravity. And that's in relation to the newfound x coordinate, or the different x, the shifted x axis. And now we're going to do a little bit of geometry. If we have theta over here, and we know that this is a 90-degree triangle, and all our angles have to add up to 180 degrees, we know that this angle right here will be equal to 90 minus theta. If this was 45, 45 plus 90 would be 135, and then 90 minus 45 would be 45. So 45 plus 45 plus 90 would equal 180, so that would work. So then we know that this line right here is going to be, this line right here will be parallel to the line over here. So this means that we know this small angle right here will be equivalent to this angle right here, since they are alternate interior angles. And now, since we know that this angle right here is 90 minus theta, we know that the angle on top over here would be equal to theta, since, again, this would be a right triangle. So the 90 degrees plus 90 minus theta, the third angle would have to be theta in order for it to add up to 180 degrees. So I'm going to draw that right here to clarify. We had our force gravity, we had our force gravity perpendicular to the x-axis of the inclined plane, and we had our force gravity parallel to the inclined plane. We know that the angle right here was 90 minus theta based on alternate interior angles, and we knew this was 90 degrees, so 90 plus 90 minus theta plus x is equal to 180. So that means 180 minus theta plus x equals 180. Subtract 180 over, so you get x is equal to theta. So we know that this angle up here is equal to theta. So now that we have that established, we can find our gravity acting in the x and the y components, because we have our theta over here. We know that cosine of theta will be equal to our gravity parallel. Let me write it over here. We have cosine theta, and cosine would be adjacent over hypotenuse. So in this case it would be force gravity in the y direction, right here, over our hypotenuse, which is our force gravity, and then we get Fg cosine theta is equal to our force gravity in our y direction. So we found our force gravity acting in the y, but for this problem in particular, we're going to be worried about the force gravity in the x. So we have sine theta, which would be opposite over hypotenuse, and that would be this line right here, which is our force gravity, which is parallel, which would be in our x direction. So force gravity x over our force gravity, our original force gravity vector. So we have force gravity x is equal to Fg sine theta. All right, so now we found our gravity in our x and our y. I recommend that you just remember force gravity on the x along the inclined plane is Fg sine theta, and that in the y is Fg cosine theta, although I can't really think of an example where you'd use gravity in the y direction. Okay, so now we have force gravity acting in the x direction, so we have Fgx, and we also have a force tension acting on the object, since it is being pulled by the other object. That's what causes the mass 1 to move to the right. So now that we have all of our forces, let's start using Newton's second law in order to solve this. So we have summation in the forces in the x direction for m1 equaling force tension minus force gravity in the x, which is going to be equal to the mass 1 times acceleration according to Newton's second law. And realize that I took force tension first and subtracted force gravity from it because force tension is being impeded by force gravity, not the other way around. Since it is moving in the direction of the acceleration, our acceleration is in the direction of force tension. Force gravity in the x must be subtracted since it is in the opposite direction of the acceleration. It is impeding the acceleration. So now we're going to write that as force tension is equal to m1a plus force gravity of x, which we found as fg sine theta. We just substituted that. Okay, and now we're going to do the same with our mass 2. We have summation of forces in the y for mass 2 is going to be equal to our mass or force gravity minus force tension, again for the same reason, since force gravity is in the acceleration same direction, that is subtracted by force tension, which is impeding m2a. So we have force tension equals force gravity, which is m2g minus m2a. And the reason why I'm putting force tensions equal to each other is because we're going to set the force tension equal to each other in both of the objects, since we're assuming in our perfect physical world of physics, that made no sense, but our force tension along the entire system, along the entire chord, is going to be equivalent. So the force tension acting on M1 is equal to the force tension acting on M2. And it's kind of like how we know that the acceleration of M2 is equal to the acceleration of M1. We're using the same logic in a certain case. Okay, so now we're going to set these equal to each other. So we have M1A plus Fg sine theta equals M2G minus M2A. And you want to put the components with the acceleration a together and g together. So you have m1a plus m2a equals m2g minus fg sine theta. So pull out an a and pull out a g. And I'm going to divide both sides by m1 plus m2. So I have acceleration is equal to g, m2 minus fg sine theta over m1 plus m2, and we derive the equation for our acceleration. And notice that for this problem, as in with every single Pulley problem that you ever encounter, acceleration is equal to a fraction of g. Since we're subtracting our masses on top and we're adding our masses on the bottom, that means whatever answer we get will be a fraction of g. So if there's no way that I can get acceleration equal to or greater than 9.80 meters per second squared. It's impossible. You cannot have a free-falling system in a Pulley system, or a free-falling object in a Pulley system. No matter what my masses are, no matter how great mass 2 is, and no matter how small mass 1 is, I'm always going to get a number for acceleration less than 9.80 meters per second squared. And there you have it.